Alright, so today I'm going to teach you about partial fractions decomposition for integration. So this is kind of a big topic, or it's not that it has a lot of parts, it's just that it's kind of a long process and there's a couple major points that need to be made. So I'm going to be breaking this lesson up into 3 different videos. So this will be lesson 1, it'll teach you the basics, and then lessons 2 and 3 will include other little nuances or major topics or major points within this topic of partial fractions decomposition. So first it's kind of best to describe partial fractions with an example. So we'll open with an example here. Say I asked you to antidifferentiate x squared plus 2x minus 7 over x squared plus x minus 6 dx. So we couldn't really do any kind of u substitution. There's no quotient rule for integration, so we're kind of stuck. So we need to use a new technique. So we're going to use partial fractions decomposition. So basically what we're going to do is we're going to convert this big, heavy, cumbersome rational function into, and we're going to decompose it. We're going to break it into smaller, more easily managed and more easily integrated functions. So to start with partial fractions, the degree of your numerator has to be less than the degree of your denominator. So here they're the same, so what we're going to do is we're going to do some long division, that divided by that, and to kind of break it down a little and simplify it. So if we do some long division, we'll set our denominator on the outside, so x squared plus x minus 6, and on the inside we'll have our numerator x squared plus 2x minus 7. So long division, it works, it's the same way for polynomials as it does for regular numbers. So what do we have to multiply x squared by to get x squared? Well, just 1. Okay, and so what will happen if we get that? We'll have x squared and 1 times x, so plus x, and 1 times negative 6, so it'll be minus 6. And we're going to be subtracting these. So x squared minus x squared, well, that's 0, so they cancel. 2x minus x, that's x. And 6x minus negative 1, sorry, minus 7, negative 7, sorry, excuse me, negative 7 minus negative 6, well, that's negative 7 plus 6, which is negative 1. So because the degree of this is less than the degree of that, now we can just make this our remainder and put it over our denominator here. So it'll be 1 plus x minus 1 over x squared plus x minus 6. So these two things here are equivalent expressions. So we can make this a little easier. So the integral of this integrand here is the same integral of 1 plus x minus 1 over x squared plus x minus 6, all with respect to x. So there is a sum and difference rule for antidifferentiation, so we can break that up and make it look like this. So, well, the integral of 1 dx, well, that's just x. So that's going to be this easy part. So right now we're not going to worry about this whole integration. We're just going to focus on manipulating our integrand until we can get it to look like something we can work with. So let's start just here with our integrand. So I'm going to make a claim that there are two numbers, a and b, such that a over x plus 3, which is a factor of our denominator, plus b over x minus 2, which is another factor of our denominator, that a and b, such numbers exist that a over x plus 3 plus b over x minus 2 equals our integrand here, x minus 1 over x plus 3 times x minus 2. Alright? So let's find out what a plus b equals, or a and b equal. So how would we do that? If this was just a regular fraction, I said add them, well, you'd think, okay, we have to have common denominators. So we would have to multiply this side, a x plus 3, by x minus 2 over x minus 2, right? x minus 2 over x minus 2. And then we'd have to multiply this side by x plus 3 over x plus 3. X plus 3 over x plus 3. And then we still have our other denominator, x minus 2. Right? So now they have the same common denominator, so let's just combine them. So we have a times x minus 2 plus b times x plus 3 all over this single common denominator of x plus 3 times x minus 2. And this is equal to our original function here of x minus 1 over x plus 3 times x minus 2. Now, okay, so we've gotten here. What next? So our denominators are equal, so we can cancel them out. Denominators on opposite sides of the equal sign can be canceled out. So then we're left with x minus 1 equals a times x minus 2 plus b times x plus 3. Alright? So how can we solve for a and b? Well, what we usually do is we pick convenient values for x so that they make either a or b disappear, and also at the same time make x disappear, so then we have one equation and one variable which we can solve. So convenient values for x would be a value like x equals 2. Because if x equals 2, then we'll have 2 minus 1, so that'll be 1, equals a times x minus 2. Well, x minus 2 is 0, so I'll have a times 0 plus b times 2 plus 3, well that's 5. So this will become 1 equals a times 0, that's just 0, plus 5b. And so then we can show that divide both sides by 5. So 1/5 equals b. Alright? So we have that. Now, how are we going to solve the next part? Well, let's pick another convenient value for x. So what value, notice how when we picked x equals 2 it made this 0 which made our a disappear. So what number would make this disappear? Well, x equals negative 3, because then this would be 0 and b times 0, that's 0. So let's try x equals negative 3. So then we'll get negative 3 minus 1, that's negative 4, equals a times negative 3 minus 2, that's negative 5, plus b times negative 3 plus 3, that's 0, so b times 0 is 0, so we can just kind of ignore that. Okay, now let's try solve for, let's kind of make this, pretty this up, so we'll have negative 4 equals negative 5a. Divide both sides by negative 5, so we get 4/5 equals a. Sorry, equals a. So we can go back and plug in these values we have for a and b into our original equation. So our original equation up here stated that a over x plus 3 plus b over x minus 2 equals our integrand, right? So if a, like we said over here, equals 4/5 and b equals 1/5, that would make this look like it equals 1/5 over x plus 3 plus, sorry, a equals 4/5. So 4/5 over x plus 3 over 1/5 x over x minus 2. So this is much easier to integrate. So instead of having our integrand look like this, let's rewrite this using what we know, that this is equal to this now. So our integrand, our problem suddenly has become the integral of dx, same as integral of 1 dx, plus the integral of 4/5 over x plus 3, plus 1/5 over x minus 2, all dx. Now there is a constant multiple rule where we can take constant multiples out of our integrand, and a sum and difference rule where we can split up our integrand into sums. The integral of a sum is equal to the sum of the integrals. So this will now look like the integral of dx plus 4/5 the integral of 1 over x plus 3 dx plus 1/5 the integral of 1 over x minus 2 dx. Now these are all very easily integrated. So the integral of dx, well, that's just x, plus 4/5 the integral of 1 over x plus 3, that's ln, or the absolute value of x plus 3, and that's just u substitution right there. I made a video on that if you want to check that out. Plus 1/5 the ln of the absolute value of x minus 2. So this is, and then all, of course, plus our constant of integration. This is equal to that. So yeah, it's a complicated looking answer, but it is kind of a complicated problem, and that's just how partial fractions work. So there's two other things you need to know when doing partial fractions decomposition, and we'll cover the next one in the next video.
I'm Stuart Jeffries. I'm a professor in physics and astronomy at the University of Hawaii, and I'm associate director here at the Institute for Astronomy on Maui. What I do is I'm a researcher, and I research into solar physics and also imaging.
Apart from the obvious applications of higher math, like in science, technology, engineering, those kinds of problems, how have you benefited from your education in higher math?
Okay, well, I'm not sure whether I've benefited, but maybe my kids that I coach swimming have benefited. One of the things I do is that I do a lot of measurements of my swimmers in the pool, measuring their velocities and their stroke rates and things, and I analyze their data. And one of the things I do is I use calculus. I take derivatives of the data and I look at instantaneous stroke rates and things like this. And the idea is that I want to be able to tell these kids what their optimal stroke rate is for each distance they race, and we can train at those optimal rates. And so, as I say, I make a lot of measurements, and I use this type of math to help me analyze it. So whether it's helpful, you'd have to ask my kids, but I do know that their times are getting faster, so maybe it's helping.